In the last segment, we saw how to define a maximum entropy or exponential model which had parameters which were the weights of the various features. In this segment, we're going to look at how we can set those parameters so as to maximize the likelihood of observed data. The log conditional likelihood of a maxent model is a function of the observed data, the actual datums and their classes, D and C, which we assume to be independent and identically distributed, and the parameters lambda of the model. And it has the form that we see here. So this here was the same form for the model that we saw in the previous section. And what we can see is that in principle it's straightforward to work out the log likelihood of some data, but it's only going to be easy to do in practice if the number of classes is reasonably modest, because we're summing over the classes here. And we'll actually come back to that issue later in this segment. We can take this log likelihood and separate it out into two components. So here we have what used to be the numerator, and here we have what used to be the denominator. So we can say that the log likelihood of the entire model is a difference between the log likelihood of the numerator and the log likelihood of the denominator. The derivative of the numerator is really easy to work out. We start here with working out the partial derivative of the numerator with respect to each parameter of the model. And so this is the numerator over here. And well, first of all, we see that the log x just cancels out because they're inverses of each other, which gives us the form over here. And then we simply move the partial derivative inside the sum, which we can do twice. We can then move it in here. And then we ask, what are the partial derivatives with respect to these lambda I fi terms? Well, the partial derivative with respect to lambda I is going to be 0 except for the term that involves lambda I. And so then the partial derivative for that term is simply fi of cd. So by summing that up, we get the numerator. And the thing to notice here is that the numerator actually has a very simple and intuitive form. So what this is calculating is precisely the empirical count of feature fi. The derivative of the numerator is just this empirical count. Working out the derivative of the denominator is a fraction more complex. You actually need to remember a little bit of calculus for this one, but it's not that hard. So here we have taken the denominator term from before, and we're taking the derivative of it with respect to each parameter weight as a partial derivative. So now, first of all, we can move the partial derivative inside the sum, but then we need to take the derivative of the log of something. And so to do that, we have to then use the chain rule. So the chain rule is that you take the derivative of the outside function times the original function times the derivative of the inside function. So the derivative of log is the 1 on x function, so we get 1 on x of the original function here. And then we take the derivative of the inside function right here. Working then on that right-hand side, we now can move the derivative inside the sum again, and then we get the derivative of the x function. So at that point, we have to invoke the chain rule a second time. So the derivative of x is itself, so then we have x times the inside function here, and then we take the derivative of the inside function over here. Okay, so at this point, to go down then to the next line, what we're doing is we're regrouping these two terms, and that gives this part over here. And then on the right hand side, we're still working on the derivative of this function. And while this time this function has the same form we saw in the numerator, since we're taking the derivative of this sum here, that the only term that's going to be non-zero is the one that involves lambda I, and so then that term in the derivative is just fi of c prime d. And so what we end up with here is this term looks exactly like our model. We've got the same exp for a particular class over the sum of the exp of all the different classes. So what we have here is the model probability of class C prime, and then here we have the function, the feature value on the value C prime. And so what we're getting out here is the model expectation, i.e. the predicted count of Fi given the parameter weights lambda. So putting those two parts together, what we have is that the derivative of the log likelihood with respect to a particular parameter lambda I is simply the difference between the actual count of that feature minus the predicted count of that feature according to our current parameter weights. And well, how do we maximize a function? We maximize a function in the standard case at the point at which its derivative is 0. So we want this difference to be 0. And so that, in other words, is saying that the optimum parameters of the model are found when the model's predicted expectation equals its empirical expectation. So this optimum is always unique. The actual parameter values that give it to you may not be unique, but the value that is the maximum of the function is unique because we have a convex function. And providing you estimate your models from real data, it always exists. This is something I'll come back to later, but these models are also called maximum entropy models because we find that what we're actually doing is finding the model that has maximum entropy while satisfying these constraints on the expectations. Okay, now we know about working out the partial derivatives for the conditional log likelihood function. So to recap, what we then want to do is choose values for the parameters lambda 1, lambda 2, etc. that maximize the conditional log likelihood of the training data. And what we find is that the way we do that is to make use of these partial derivatives. In particular, if we take the vector of all partial derivatives, that gives us the gradient of the function. Let's see that in a picture. So here we're imagining that we have two parameters, lambda 1 and lambda 2, and depending on the settings of those parameters, we get different values for the conditional log likelihood. And if we map them out, we get this kind of likelihood surface. So the idea of what we want to do is we're going to start with the lambda 1 and lambda 2 set to some value, and we're going to calculate the derivatives, the partial derivatives at this point. And those partial derivatives give us the gradient, the direction of steepest descent on this likelihood surface. And so we're going to walk in that direction a little, calculate the gradient again, walk in the direction of the gradient a bit, calculate the gradient again, walk, and we're going to head off and come to the maximum value of the conditional log likelihood function. So for maxent models, this log likelihood surface is always convex and has a maximum. But while it looks fairly easy to maximize in this example, in the real problems we deal with there might be hundreds of thousands or millions of parameters, and so it's considerably more difficult. So how we solve that problem is that we find a good numerical optimization package and get it to find good parameter values. In particular, let me just note that commonly these packages, including the one that we use for the programming assignment, actually are minimizers. So instead you minimize the negative of the conditional log likelihood, which is equivalent. Now there are many numerical optimization techniques. The simplest is gradient descent, which just says that you walk always in the direction of the gradient. A variant of it is a stochastic version, stochastic gradient descent. This one is actually quite effective and is still often used for big problems. In the early work on maxent models in statistics and NLP, people commonly used iterative proportional fitting methods like generalized iterative scaling or improved iterative scaling. These aren't used much anymore though. Other standard numerical optimization methods like conjugate gradient are quite effective, but the method of choice that's usually used these days is quasi-Newton methods. In particular, one well-known algorithm is this LBFGS algorithm, which is the one that we use in our assignment code. And that's a good method to use in general. Okay, so I hope that means you've now got a good sense of how to calculate the partial derivatives of the log likelihood function and understand how that can be used to find the optimal parameters for the model.